Dr. Gopu R. Poti, Professor, Department of Ocean Engineering, University of Rhode Island, USA. May I now invite Shri Mohan P. Matthew and Dr. Gopu R. Poti onto the dais.
Experiences. She is working as a scientist in the Ocean Electronics Group of NIOT in the research projects. Now, how much time are you likely to take? 12. Okay. So we will have a 2-minute question and answer session also towards the end. Please.
because of the technical difficulty, there will be some delay, so probably we can break for some tea and then come back in 10 minutes. 10 minutes. Okay? So, tea break, 10 minutes.
welcome back. Let us start the session without delay. Yes, we'll have the first speaker. Thank you.
Good afternoon, everybody. I'm Sri Shah. I'm working as Project Science Project in Institute of Ocean Technology. My topic today is performance analysis of linear recursive adaptive filter to mitigate multi-parameter effect. Here is an outline that I'm going to discuss as I run through the presentation. I'll give you an introduction about the adaptive filters and the system configuration that is work and filter structure and the algorithm which is used and a little bit about training filter and some simulations and final conclusions. What adaptive filter does is it generally operates in an unknown environment and it will track time variation input. That makes it self-adjusting and time varying and non-linear. They find applications in various areas, including processing and control systems. Adaptive filter work is it works on the channel output and the cascade of the filter and the channel will provide an ideal transmission medium. Basically, what it does is it will mitigate the distortion introduced in channel. How it does this is by training itself to the input variations. And the use of these filters in underwater acoustic channels is done usually because underwater acoustic channels are highly stochastic, and we all know that the main distortions that are introduced are noise, attenuation, time varying part, and Doppler effect. For lessening these distortions introduced in underwater channels, we can use these adaptive filters. This is the basic system configuration of a generic adaptive filter. It basically has a structure which is a transversal FIR that I have used here, and it has an adaptation algorithm which is RLS here. What it does is it takes in the input and the filter will give an output which is compared with the desired, that is a training signal, and the error is given as input to the adaptation algorithm. The adaptation algorithm will work on input and error and sets the weights of the filter. Thereby, the filter will change its weight as per the input. Here in this work, I have used a transversal filter, which is nothing but a daylight filter. Why only this is it best suits the multi-part kind of environment. So it is just input is directly by the tap coefficients, and then output is generated. That is the filter structure. That is the upper block. If you see the upper block, this is basically that input into the waves. If you see the lower block, which is the adaptive algorithm, which is here I have used recursive quest algorithm. Here, if you see the equations that are run in background algorithm, we can see that if x of n is if u of n is an input signal, then first a gain vector is calculated. Gain vector will depend on an correlation matrix P of n and the input, and an estimation error is generated. We will use this estimation error and the gain vector to update the tap. That is the weights of the filter. These weights are once again used to update the correlation matrix. This loop will go on till train the filter. This signal graph actually shows the same equations of RLS will update. So as long as we train the filter, this flow goes on and the waves will change accordingly. But to start off, we have to initialize the algorithm, for which I have used, there is a parameter called lambda, which is a forgetting factor, which basically is how is the memory of the algorithm. To what extent the signals it should memorize. This is basically close to unity but less than unity. I have taken a value of 0.99 here, which is usually used. And also we have initialized correlation matrix, which initially I have taken as identity matrix, and a weight vector with a zero vector to start off. With these parameters, we start training the filter and finally arrive at final phase where the training will be stopped and the filter has to be reached, and then directly the filter output will be taken as a channel, will be taken for demodulation. Now, what is the signal that can be used as for training? Generally, MLS or pseudo-non sequences are used for training these kind of filters. I have used a maximum MLS sequence. MLS sequence is nothing but a periodic binary sequence of zeros and ones. This can be generated by generated polynomial G, for which the equation is given here. The length of the sequence is dependent on how much is your delay spread. Since I am talking majorly about the multipath introduced, if you have an approximate estimate of the delay spread, you can set your training sequence covering that delay spread. I have used a degree 8 sequence. I will show you why I have used also that for training this filter. Coming to the simulation part, the first picture shows the simulation scheme that I have used here. The input bits are BPSK modulated and pass through a Rayleigh fading channel wherein air noise is also introduced, which is then passed through a adaptive filter, which is RLS adaptive filter, and the output is demodulated to get the data output. The performance of this filter is measured in terms of bit error rates. I will show you the comparison between bit errors without using the filter and using the filter. Here for simulating this filter, I have used data input of 79 bits, in which 255 bits are used only for training. That is, these 255 bits of sequences will be known to the filter, and the filter trains itself in that sequence. After that, the task will be reached, and then the filter is run for the next 1024 bits which are followed after this training sequence. The modulation is BPSK modulation. I have used a 20 kHz carrier wave and 200 kHz sampling. The channel here is simulated using a multipath MATLAB object which is already available, where we can set the number of paths. I have taken 3 paths, that is 1 direct and 2 reflected paths, and I have set the delay length as shown. And I have taken the delay spread maximum to be 3 milliseconds with the path loss of as shown. The filter tags initially are taken as 20, that is, there are 20 ways to be adjusted, and the training signal is a MLS sequence of degree 8. When I run this setup, I can see that the RLS filter, which is a counterpart of the LMS filter, it converges in just hundreds, not only less than 100 samples. If I take almost 7,650 samples. So, if you take adaptive filters, there are only 2 kinds of algorithms that are available, basic algorithms I mean, which is RLS and LMS. So, compared to LMS, RLS converges in 1/10 of the time. What it basically gives us is a training overhead which is very, very minimal. Training overhead is that part which is used to extract the channel information and which is followed by the data that is actually sent. the minimum it is, the more efficient the department will be. So, RLS helps in having the training overhead lessened very much compared to LMS. Only disadvantage is RLS is a little bit computationally complex than LMS. Now, coming to the bit errors that I have been talking about, if I take the same setup and compare the bit errors without the filter, we can see that it is almost 50% of the bits are errored, and these values are taken over 200 independent simulations. This is an average value of 200 simulations run independently, and if you see that RLS gives you an bit error rate of just 10%, and LMS is a little close by. Now, for a different scenario of channel, we have taken a field case from a literature, and here I have taken a channel response as shown in the figure. Here, the delay spread is just in a span of 0.5 millisecond. That is in 0.5 millisecond duration, we have 6 echoed paths. This is actual channel impulse response that is taken at a depth of 2,740 meters. In such scenarios, how the filter performs is as shown in the below plot, which is the BER plot. We can see that if we maintain an SNR of 20 dB, the BER is almost 0. So, I would like to conclude that this kind of adaptive filters will help us in fighting this multipath and AWGS noise distortions, which are generally introduced in acoustic signals. And not only that, we have seen in our simulations that it combats Doppler shift also to some extent. And also that compared to LMS filter, RLS filter has faster convergence, almost an order less than LMS, which will save training overhead, as I have already told, considerably. And also, there are 0 bit errors if we maintain SNR around 20 dB, as shown in the field case. So, this seems to be a good option to neutralize the effects which we generally encounter in underwater acoustic channels. Thank you. Any questions? Yes.
Good afternoon, everyone. I'm Mark, National Institute of Ocean Technology. The topic I am going to present here is optimum statistical critical technique for multi-beam data processing. The outline of my presentation will be like this. The main objective here is to reduce the center beam pattern effect which is present in the multi-beam data data. Here, in order to reduce that thing, we are applying gridding. That is covered in purpose of grid. Then in study area, we have spoken about what study area I have taken for this study. In data collection and processing, the multi-beam system for this study and post-processing software used in gridding techniques. I have used gridding techniques for this study. Then results from those techniques are shown here. In conclusion part, I will show which grid technique is the optimum one. References which are used. In objective, in fact, that multi-beam systems are capable of recording acoustic signals from wide sea floor. Because of wide coverage of sea floor, large quantities of data will be recorded. But while occurring, center beam pattern will be there. So we made our objective to find the optimal gridding technique with the optimal grid size. That will result in direction and center beam pattern effect. Why I am gridding is, as I told earlier, the amount of data generated by system is very huge quantity and it depends on ping rate. Suppose for systems which goes up to 30 Hz and the number of beams vary from 100 to 300. Therefore, incoming data can reach up to 30 points per hour. In my case, it reaches around 10 points per hour. So reducing the data is necessary. Because of large data and most of the data is contribute to more detailed approximation. So data collection scans down to 5% original data size. So significant loss of accuracy can be performed, which is done by increasing the grid interval distance. Then we know what is the most the frequency size will be more. This could effectively reduce incidence angle effect on capacity distribution. But the density of data was so it will we have to consider grid method and sensor size to grid back data and reduce center beam pattern effect. So we should be very careful using grid method and sensor size. Otherwise, the gridding process sometimes smooth the data may loss information about the sea floor properties. Study here I am showing that rectangular box survey location is in option 9. It is a 40 kilometer long land survey line I have taken. In that 40 kilometer long land I divided regions into five small transacts, region 1, region 5. And multiplies collected using EM100 echo sounder. It generates full beams per ping and it's in addition to it also provides wax data that is for study of spatial distribution of fine scale sea floor of the natural pattern. Then in post-processing, I have used proprietary software by Innova because the angular dependence strength it is persistent in black images characterized by strong vertical incidence angle, which is called native shaping. In order to use that native shaping, we are using proprietary software, which is having 4 modules. Module 1 is for remove corrections like slope correction, heading, position correction and all. Module for reducing the angular effect in a coarser manner, and module 3 which will do the same thing in a final, and module 4 is for they will module low pass and high pass not remove the noisy back signal. Here in this figure, I am showing backscatter across transact lines before and after corrections. The grey color is the grey one is after correction and the Dark one is the before corrections. After this is software. This applied correction affects only first order such as the mean. So the not static distribution is for classification is a problem. So solution for this is to grid the data using an armed method and cell size. So smoothing of classification value depends on grid cell size, and the process can also value information about property. The space variable classification will be inversely proportional to the cell size. So smaller the cell size, greater spatial variability. Here the grid cell size I consider are 1.5 meter, 5 meter, and 7 meter. Are the cell sizes taken for this study? And the grid techniques I have applied for this mean, most frequent and maximum techniques to grid data. The back values to be the mean, most frequent and maximum of all back values are initial grid points, which is lying inside the resulting grid cell size. Here I am showing the results of those grid cell size for 3 grid methods. The first one, figure 3, is showing for mean method, and figure 4 is using most frequent, and figure 5 is for maximum grid method. In all figures, if you increase the grid cell size, the standardization of back strength and swap will reduce, and in mean grid method only it will become just like more uniform, whereas in most frequent and maximum it won't be like that for 5 meter grid cell sizes. So we can't confirm this 5 meter as the optimum and mean grid method as the optimum. So I have generated back images for those mean method and most frequent and maximum method. And also I have increased the grid cell size to 7 meters in order to check whether 7 meters is the optimum or not. This is the back images of region 1 and 4 using mean grid technique. Here I am showing only for region 1 and 4. Top one is for 2.5 meters. Here the maximum back strength is minus 42, whereas for 5 meters is minus 46. And for region 4, for 4.5 meters, the maximum back strength is minus 50, whereas for 5 meters is minus 57. Here are some 5 degrees back strength results, and also central part also reduced. This is for most frequent technique. Here, for region 1, this is the side, the maximum back strength is minus 40 dB, whereas for 5 meters is minus 42 dB. It shows some 2 dB reduction only. For region 4, it is 1 dB reduction only. And for maximum technique, there is no change at all, from 2.5 to 5.5 meter. So from this backscatter images of 3 techniques, we can consider optimum method as mean grid method. Then we have to consider which one is the optimum grid cell size. For that, I move on to 7 meter grid cell size. Here I am showing for region 1 and region 4, all 7 meter. A and B is for mean grid method. C and D, figure C and D is from most frequent, and E and F from maximum method. If you increase the grid cell size, here in center you can see the loss of information is there, and totally deviates from 5 meter grid cell backscatter image. From histogram also, A and B is showing for mean grid technique, and D and E for A and B is 4 meter, and D and E is for 5 meter, and C and F for 7 meter. While seeing from first two things, the pattern is somewhat similar, but for 7 meter we can see the range of value, loss of value is observed. It shows the loss of information in that data. So it is observed that maximum backscatter value is reduced to an average of 4 dB in mean grid cell method, whereas for most frequent method, the reduction is up to 2 dB only with grid cell size of 5 meter. In maximum grid method, there is no change observed with the increase in crystal size. So, when, in order to know the crystal size, we increase to 7 meter, it is observed the loss of information. Thus, the mean crystal method with 5 meter crystal size is observed to be the optimum one, which is specific to this data set. We can't do the same thing for the different data set. It may change. With the use of optimum grid technique, it is possible to get an enhanced MBS data with reduction in center beam pattern effect. These are the references I have taken for this study. Thank you.
Good afternoon. I'm here to give the presentation of the paper entitled Genetic Selection and Parameter Optimization for an SP-based underwater classifier. Underwater classification is a very difficult and challenging task due to the variability and diverse noise that are in the ocean, and the hydrophones receive their signals that are hidden in an acoustic jargon, so it's very difficult to estimate them. So what we require is a reliable target classifier which has got online information processing ability. Underwater target classification, like any other target classification algorithm, it aims at identifying underwater target classes of interest. And for the classification problem, it comprises of two major steps. The first one being to extract the acoustic signatures of the acoustic event by using a suitable feature extraction algorithm. And the second one is to use a pattern recognition algorithm onto these extracted features to find the acoustic targets of interest. In this work, we are using a support vector machine-based classifier for the pattern recognition part. Now, the performance of the classifier depends upon two parameters. The first one is the algorithmic parameters, and the second one is the feature extraction method that is being used. And in this work, we are attempting on a genetic algorithm-based parameter optimization and the judicious selection of the kernel function for the SVM classifier also. Support vector machine classifier is a supervised classification technique and statistical classification method basically designed for binary classification. It stems from the theory of structural optimization and it was developed back in 1992. There are three ideas on which we relies upon converting complex classification tasks into one. The first one is to map the data to a high space so that a classification problem in the space converted to a linear one gets converted to a high space. And the second one is to use only those training patterns that are near the surface. Therefore, there are support vectors for classification. And the third one is to find the optimal settlements in hyperplane, which is the hyperplane having the maximum margin with the support vectors. Now, in case of linearly separated classes, the learning problem can be expressed as follows. Now, we have a non-linear dependency between a high dimension vector x and an output y, and we don't have any priori information on this. All we have is the data set, and if they are linearly separable, then the linear separation height can be represented as an equation, and margin can be calculated to be 2 by norm of W. Now, our aim is to find the maximum margin classifier is to maximize the margin by norm by W, or in other words, you can minimize norm of W by 2. Now, we have two classes data, and you can have a linear separation hyperplanes, but what we need to find the optimal hyperplane with the largest margin. So, the learning problem can be set as follows. We have a quadratic optimization problem that is to minimize norm of W by 2 subject to linear constraints that defined by inequalities. Now, this was the case when patterns are linearly separable. Now, in case the pattern is non-separable, as in most real-time applications, what we do is that we map the data from the original space to a high-time space where it will be linearly separable. And this is done using Cornish function. So in short, we map the data to high-time space where so that the non-linear data gets converted to linear data, and this is accomplished through Cornish functions. Now these are some standard Cornish functions: linear, polynomials, and SVM was originally proposed as a binary classification problem, and later on it was extended to multi-class problems. And to solve multi-class problems, what we did that we decompose the multi-class problem into binary classification problems. And there are two approaches. One is one approach, one is installed approach. The first approach, we construct SVM classifiers for all pairs of classes, and in the second approach, each classifier decides distance between one of the labels to the rest. Now, we are using a genetic algorithm for the SVM parameterization. Genetic algorithm is an instance-inspired meta-heuristic algorithm which is formulated by the abstraction of the optimization process of biological evolution based on Charles Darwin's theory of natural selection. It was developed by John and Alice collaborators in the 1960s. Now, the governing rule behind genetic algorithm is the same as Charles Darwin's theory, that is survival of the fittest. And here, a particular gene represents one possible solution to survival. And we have an evaluation function, that is the fitness function, which will judge whether the gene has to go into the next iteration or not. So each solution is evaluated by a function that acts as a judge. There are two major operators in genetic algorithm. The first one is crossover and the second is mutation. Now, new solutions are used in each iteration of the crossover. And this we have two pairs, and we produce offspring by mixing genes of the parents. And variability in solutions achieve mutation. And in mutation, we alternatively add some small random value to the genes. And the next generation is formed by selecting parents and offsprings according to their fitness values. This is the general approach of genetic algorithm. We initialize chromosomes, we apply genetic operators, crossover and mutation, and we calculate the fitness values, and depending upon the fitness values, we determine the next generation, and if the stopping criteria is not met, then we review the iterations. Now, our database consists of 114 real backpackers signals of class acoustic targets, and we are using a 1 installed class classifier with MFCC and extractor. And we have to find the one function, the parameters chosen to one function, and the parameters for SVM classifier, and found using genetic algorithm. And in our work, we have employed scatter crossover, in which random binding vector is created, and the values of the random binding vector will determine which parent gene is selected in which child gene. Now, for mutation, we are employing a mutation. And for selection, we do the next generation. We are using a rule-based approach in which the area of section corresponding individual is proportional to the fitness value, and the random number generated until 102 segments span random number will be selected. And these are the parameters that we are trying to optimize using GA. The performance is calculated for variety of population size, and this function is calculated as number of classified data to number of correct classification, and we try to minimize 6+ function. The stopping criteria is either the maximum number of iterations or the related change in fitness value is less than the standard limit. These are the results that we have got. Conclusions: the performance of the classifier depends upon the parameter setting, and we are using a GA-based approach for automatic parameter selection, and is giving reasonably good classification accuracy of about 70% when classification. Thank you.
Do you have any questions for the speaker? Questions? What was the cost function you used?
It's a number of misclassified data to number of correctly classified data.
Number of correct classification. Okay.
Thanks.
Thank you. So we'll move on to the next talk. The talk is sonar image using adaptive processing of local patches. Authors are Ritu James and Supriya Amos. Speaker is Ritu James from Department of Economics.
Good afternoon. My topic is sonar image using adaptive processing of local patches. So, image denoising in case of sonar is a key preprocessing step, and basically the sonar images formed have a sparse representation. So, I exploited the decorrelation techniques of PCA and SV in my study. I have initially considered the whole image. Then I have taken patches of image, and finally blocks of patches. So side-scan sonar images is basically affected with multiplicative noise, usually known as spectral noise, and it's a signal-dependent noise model. So when we do the homomorphic filtering approach, you can convert that multiplicative noise model into an additive model. So you will see that you have log transformation converting that into an signal independent additive Gaussian noise model. So I consider each string of data being signal is given, and it is considered as the number of rows, and now the sensors considered as the number of columns. So basically I have done the PCA. The basic concept is you have a set of observations of correlated variables. After applying PCA, you get the linearly uncorrelated variables and known as the principal components. Usually the principal components are the eigenvectors of a covariance matrix. Moving on to the singular value decomposition, it is again you have the real or complex matrix, and its linearly independent components you get, and finally it's actually you have the energy getting packed into a few number of coefficients. So this is basically if you have an m by n image, you have u which is consisting of singular vectors. V is the right singular vectors, and S we have is a diagonal matrix which is having the singular values as the element values. So your left singular matrix is m by n. Here you have an image of m by n size, and the right singular vector will be of n by n size. And basically, when I consider my whole image, I have taken the left singular and right singular value. But when I want to the patch-based processing, I have taken the left singular values. So PC and SVD, why I use sonar imaging is, as I told you, sonar images are the real side scan sonar images. When we do the classical approach for denoising, most of them are low-pass filters. It will correctly remove the spectral homogeneous areas. But when we move on to the what happens is we have information in high heterogeneous target areas of the real side scan sonar images. So when we go with classical adaptive or even labeled filters, then we have a fixed basis, we will be losing that high frequency information. The advantage with the PC and SVD is, it will generate a two-dimensional basis set which have vectors lined up along edges and not echoes them. So we have high frequency coefficients caused by the edges are much smaller. So when we discard the unwanted coefficients, we won't use the high frequency coefficients. So in this case, we can say that edges are retained in the denoising algorithms. So basically, when we move the patch-based processing, we decompose the image and get the principal components, then we denoise the principal coefficients and finally reconstruct. These are the basic steps which are done. Initially, take the original observed image, we will calculate the noise variance of the image, then we will partition that image into n by n patches. So I can say my training vector, which is consisting of which makes the race matrix, may have a vectors of size n square by 1 arranged or concatenated to the right. So you have m columns depending upon the number of patches. Then I will find the PC functions, basically the eigenvectors of the transpose matrix, and each eigenvector represents the principal components of corresponding training vectors. Then I project my training vector on the base functions. Basically, functions are the eigenvector. Then I used for calculating the variance of the patch. I have used the maximal estimation. The equation is given there. And to denoise these coefficient functions, I have used these minimum error estimator, where I have assumed that my multiplicative noise is converted into an additive independent Gaussian noise model, and I could say that yi is my observed image, xi cap is my estimated image. So I use that sigma square into y. So I could get my estimated image value from the observed image. And the reconstruction is done by the inverse. And finally, the matrix is converted back to the original image. So this is for example I have taken. If this is my image A, I could get my S matrix of size 4 by 4. Then I can say this is 16 by 1 vectors and concatenated the next. So I have m patches and n square is my single patch size. Basically, we want to SVD, patch-based processing. Again, the same procedure as PC is done. Finally, coefficients in this case have taken left singular vectors. I'm not considering right singular vectors. Then finally, denoise the coefficients. Again, apply and reconstruct. In block-based PC and SVD, instead of going patches, I have taken groups of patches formed into blocks. And the similar procedure is done. For the blocks, I have found out the principal components, coefficients. Then I denoise the coefficients. Finally, reconstruction. So basically, these measures, we will be having only the observed image with you. And we will be estimating the noise image of the observed image. So these are all kinds of metrics used for the study purpose. So I have used the coefficient variance, number of looks, spectral subtraction index, coefficient and SMPI as the without references for the comparative study. So for the real side sonar image taken here, the noise image. I got the equal number of looks for its observed image is 5.842 and I have done the analysis with the PCA and the first two columns shows the PCA and LCD applied to the whole image. Then patches next to columns and next two columns it is the to the block it is applied. And when the analysis say that SVD is given me the maximum number of looks compared to the other methods. So these are the images. As a conclusion, I should say that if you have improved value compared to the other existing algorithms as I told you, they will remove the high frequency components not the case of pre-processing of side scans on images. And useful for the details are at high frequencies. Then the challenges were selecting optimum low or patch sizes. When you go with the high patch size, I could say that the computation speed is going to affect. If high patch size means the means the patch is getting reduced. And the improvement which I could get to this is if I could go with the variable patch size instead of fixed patch size and going with the overlapping patches, I will be estimating the single pixels for more than as I have done in my case. Grouping of similar patches block-based method would also be a better idea. If I could instead of grouping adjacent patches, similar patches, which is obviously going to offer size and images, I could get better result. These are the references. Thank you.
Any questions? What are the kind of signal to noise ratios that you look at?
Actually, I have done that because I was not having an original image. I was taking the real size scans.
The real size scans for our images, was it actual thing or
I'm taking it from there.
net? No questions? We move on to the next paper. Is underwater image enhancing single scale Setnex on a recon hardware. So others are Alex, Rajesh, and Dr. Supriya. And I believe the paper will be presented by Alex Raj. He is a research scholar in the Department of Electronics, Cochin University.
Good evening, all of you. I am Alex Raj, scholar in Department of Electronics. And my topic is broad image enhancing scale next on recon hardware. My agenda is the motivation towards this work, introduction, the next algorithm, then FPGA implementation, results and conclusion. My motivation, underwater image enhancement. We all know it actually plays an important role in several areas like video, CDMO, cable pipeline, etc. So normally, this is apart from the sonar image processing, it's actually optical image processing. What actually means is the cameras placed in front of underwater autonomous vehicles, vehicles, they do suffer so many aspects like degradation due to illumination difference that is present in the underwater scenario. So, in order to achieve that, image processing must be done before doing anything. And more than that, whenever we do some automation, some hardware platform should be there for speeding up the operation. So several has been done, and we will program the best option to have harder like image processing because of parallelism going to it because image processing algorithms often have some significant aspects whenever facial recognition like that one. So many applications will be there. So parallel will be effectively done in PG processing. My proposal is implementation of SSR in field programmable gate arrays, and I have starting with PGA and the software used in generator. And regarding the algorithm. So whenever we actually see an image, this is not actually captured by the digital cameras. So digital cameras from so many aspects, dynamic range compression. So we can see the effects when we see the shadows effects and range of colors actually render. It's very much what actually being captured by the digital cameras. And they note how this visual aspects that actually the human system is actually having. The recognition is being evolved by Edland in 1880s, and after that so many evolutions were there over this one. And majors that can be done with the sharpening, consistency processing, and dynamic range compression is the shadows. And the development of techniques are the various single-scale reconnects, multi-scale reconnects, and multi-scale with the color restoration, and with that one with the gain and offset. So these are the different developments are improving in reconnects techniques. And coming to this single-scale algorithm, RFXY is the first one is communication where the logarithm is taken and it subtracts the convolution of the FFXY where FFXY is a surround function and it is controlled with the original image. And this one, FFXY is a surround function, so the recognition algorithm actually corresponds to center surround function. So actually when we have different image, the illumination changes. What we actually see is something different from the actual color of that image. So but actually the camera taken by camera is what is mean by the camera is different from that. Now RFXY can be written as like this one. Logo SFXY RFXY by the average of that because Gaussian expression. It's actually epsilon is considered to be a value from surround function. So when we consider surround function, it's actually like average function. So we consider that one. But since the illumination, so the image is always a combination of reflections as well as illumination. And since the illumination is always a slow varying one, it's always having low spatial variation. The average value as well as one is taken almost same in this case. And then we can say that the recognition value is almost independent of the source illumination. So this is the main concept behind this recognition algorithm. And the design of surround function is one of the important factors. And earlier, the land proposed the elimination of surround function as 1 by 1 plus r square plus c square, where r is the surround root of x square plus y square, and c is one spatial constant that is actually being taken as experimentally. And later on, Herbert in 1999 they find that Gaussian function can be used as a surround function because Gaussian function is always pointing to a particular pixel and it's around the neighboring one. So that is most regional one, so that can be taken as a surround function. It will give better results for that one. That has taken Gaussian function for that one. And this is around space constant C. And the value of k exponential, the k is given by the integral of f(y) dx is equal to 1. Then after this multi-scale recognition algorithm, there is some artifacts like there are some problems, the color condition and dynamic range compression. So earlier, after this one, we have started to have different values for this C value. So different values for space constraint value, then they combine together so that they have the multi-scale reconnects. So the multi-scale means different values of C, ranging from 0 to 200 can give. For different values of C, you have different dynamic range compression, and tone division can also be changed. So by combining all these aspects, we can have multi-scale reconnects algorithm. So this one is actually the block diagram of multi-scale reconnects algorithm. And this is my post work where, so earlier in the case of single-scale reconnects algorithm or multi-scale reconnects algorithm, what happens was RGB was taken, and immediately they are processed using this formula. Then it is combined together. But the problem is that the combination by which RGB components are having to form a image is different. So when they process in the same channel, when we combine it together, we will be having some color degradation. So in order to restrict that one, so some of them have proposed RGB to HSM model, then only value is being taken. And in our method, what we have taken, since the underwater scenario is considering, so underwater always attenuates red color, so that here, what we have done is, instead of having this HSM or RGB directly, we have taken this YCCR model, and CR since it's attenuating more. The YCCR models are taken, leaving the CP part, then it is some same method, and thereby obtaining the better results. Then the same thing is implemented in FPGA. So the platform is very boot. And the silent system generator is being used. The silent system generator is used. We have the hardware oscillation is possible. The image can store inside the computer, and once the image is there, it can be taken to the vertex board through JJ connectivity. But the problem, the main challenge of this one is what problem is the system generator allows only one-time data to be processed. So we have the development data, and this has to be processed in one-dimensional form. So that's one of the major challenge. And more than that, once only after getting the results, you can view the computer. So in between those and it's very difficult to sort it out. And this is part of the system generator subsystem block where the FPGA machine is given. So here, only after getting the results, the two blocks which separate from the computer with the system generator, they deviate in out. So in between what happens, only some waveform can be seen, no picture can be seen. So it's very difficult to analyze once we get to error. So this is another part of the system generator block. This is the device utilization, and the total time taken for the computation is 24.85 milliseconds. So many LEDs and registers are being used. The advantage of being used this FPGA platform is it's recoil configurable. So it's something like an IC. So what are the things that you put in? A hardware form inside that one. So the time taken to get the output when the clock frequency is very less, the output is throughput is very high. So coming to the results, so these are actually the simulation results. Simulation results in MATLAB, known as FPGA. So the inputs are given. So C value, the space constant with the different C values, C15, C80, C215, they are given, and the output is given in the below side. And this one is a result with the multi-scale reconnects algorithm with the color restoration and multi-scale reconnects algorithm. So whenever we have the multi-scale reconnects algorithm, the C values are combined together. So earlier we have separate C values and the outputs are viewed. And here they are combined from the multi-scale reconnects algorithm. And since we are having the RGB component coming together, there will be some color problem. So in order to avoid that one, in order to restore whatever the color that we have lost, we will be using this color restoration program. Then this is hardware co-simulation results, the input image as well as the output image. This is actually being done with the FPGA. And the underwater image, so you can see some patches in the output images. This is because it has been done by only by using this single scale Retinx algorithm. So once it is sorted by using this multi-scale Retinx algorithm, the patches can also be removed. So the shadows, when we consider only the shadows, then there will be some problem with the color rendition. So tonal rendition will be there. So there's a trade-off between the tonal rendition as well as this dynamic range compression. So we have to be compromised in between. So that's why we are going for this multi-scale Retinix algorithm. So the conclusion and future work. So already the single scale it's implemented in FPGA, and in future we can have this multi-scale Retinix algorithm with the color restoration in FPGA. And these are my reference. Thank you. Thank you.
Any questions for the speaker? Okay. Looks like there are no more questions. Thank you once again. We'll move to the next talk, which is the authors are Chinchu M and Supriya MH. The title is Real-Time Tower Target Recognition using LabVIEW. And it's being presented by Chinchu M and he's an assistant professor in College of Engineering, Aramura.
Good evening, Mananwal. I'm working as assistant professor in College of Engineering, Armor. My topic for today's presentation is real-time target recognition LabVIEW. These are my contents: introduction, extraction, multi-frequency perception, block dynamics, support button machine classifier, block diagram, LabVIEW real-time, implementation results, and finally conclusion. First of all, let's begin about the underwater control system. This is used to detect underwater targets based on sequence collecting hydrophones. So mainly two parts, extraction and classifier. That is each underwater has got an acoustic, that is called as feature. Based on these features, we are classifying the signals. Feature extraction is actionable loss in areas of underwater target systems. This is crucial for application. The features can be extracted directly from the dynamic signal or transmission domain. There are different types of features are available, like frequency extraction, summation extraction, etc. This is what I am using multi-frequency scheme. Second method of extraction. This system is of taking inverse Fourier transform of spectrum of a signal. In MF frequency bands are distributed Mel scale. Equation used to convert linear signals into Mel signals given below. The reason is 259 plus 700. This figure relation linear frequency and Mel till 1000 Hz. Mel scale also above that logarithm. This is block diagram of C. Explaining each block. First of all, use the high road is, then we use framing, segmenting signals have number of frames, then windowing signal, handling use, then pass for it taken, conversion domain, then pass to Mel bank and solve a set of triangular bandbus, overlap windows, and the frequencies are aligned to Mel frequency scale. Then logarithm of Mel filter bank is taken. Then pass to transform that converts Mel domain into time domain. Output is we obtain Mel frequency capture coefficients. Then now take teachers, now get classification teachers, now major machine learning. Classification problem concerns procedure to achieve the objective of a signal. Classification has two phases, training phase and phase. The performance of classification phase commonly valued by the error. I am using support potential classification algorithms. Classification is statistically by 1992, and it is a binary classification algorithm that classifies between two classes. In a sense, it creates a hyperplane between data sets to indicate which class belongs to. It is creating an optimum hyperplane. This shows two bind classes. Suppose two classes are there. Between these can have any number of hyperplanes. We require an minimum hyperplane, the maximum margin of 10. In this, the red string diagram shows you support vectors. Support vectors are those string vectors that are the optimum symmetric hyperplane. This hyperplane indicated using H0 is the optimum symmetric hyperplane. Then kernel function. Actually, FFM is a linear classifier where you can use it also for non-linear classification also. So that we are using kernel functions. Kernel functions map the important high dimensional space through some non-linear mapping. Then linear dimensional space is constructed in that high dimensional space. There are several types of kernel functions available like multiple pairs, function, polynomial kernel functions, etc. So this is mapping kernel function. First shows a non-linear problem by using mapping function is converted with linear problem. So we can apply this. Then multi-class SVM. SVM is a binary classification program, but we can explore multi-class problems also. So that we have different segment we can do different binary classification problems using algorithms, one-dimensional approach and one-dimensional approach. These are two algorithms for multi-class classification. This is block diagram number. First of all, train extract structures and apply to SVM classifier. Then the sequence apply extract structures and apply to SVM classifier at the definition of the target. So the main aim of my work is to implement to develop an underwater target system in real time for the enhancing software real time. This lab is laboratory for instrumentation engineering department. It's a graphical programming analysis. Programming using target notation. It has two parts, run-ban and log-log. Run-ban is interface and log-log is the programming part. Lab programs are called as virtual instruments. By using LabVIEW provides two advantages, multi-threading facility and time use, so we can obtain fastest execution. In order to execute the program that we have written using real-time system, we prepare a real-time processor that should be a national instruments processor also, so that they can use different types of hardware devices like combat radio, combat bag, etc. That is, we are programming using LabVIEW and executing using real-time processors like combat radio, combat bag, etc. My work, I am using combat radio you used to execute the program, that is a hardware device to execute the program. Combat is a configurable memory control and execution system. It can accept both analog and digital inputs. It has got mainly 4 main components: controller, expansion system, and software and input module. This shows a combat video. First real-time controller. Then there is input module is there, then expansion chassis is there. In order to execute our program, we have to connect the combat to our Windows PC. That can be done using an Ethernet cable. That is, then after that, we have to detect our combat in our PC. So that we have to open Measurement and Automation Explorer. In that, under remote system, our name of combat will be displayed as shown on slide. That is 09012. That is the combat we use. Then we have to go to network settings as shown on here. Then we have to set the IP address and subnet mask. Then refresh the device. Then now the combat is ready for execution. After doing all these network settings, we have to add our program to combat video. Program that we are using real-time called VIs, that has to be added to our combat device. For that, open Project Explorer in our lab window. Then under Project Group, there our combat name with IP address shown. Right on that. Then add our program to combat video. Then open the file and run the program using combat video. So all these settings I have to do. Then implementation and results. I can implement simulation system using lab real-time. Lab software implementation consists of 2 parts, mainly feature extraction and support machine classification. My aim is classified between 4 targets, that is class 1, class 2, class 3 as shown in figure. That I have used data results, 100% I use, 70% for training purpose and 25% for testing purpose. Figure shows plot of mathematical coefficients obtained for class 1, then for class 2, class 3 and class 4. This shows program number of MCC, that is the program that I am going to obtain mathematical coefficients. First of all, I am having Gaussian, fast Fourier transform, then I have used steady filters, then logarithm and inverse Fourier transform. Then shows implementation of support machine classification. I have used 2 kernel functions in here, RF kernel and memory kernel. With the RF kernel, I have 83.3%, and the memory kernel ratio, it is 6.67%. This shows the rate for both of these kernel functions. Conclusion. Under what classification software environment does, performance of any classification system depends on classification algorithm we use and the structure to identify the acquisition signature. This is I have a simulation of real-time target recognition system using LabVIEW. Since LabVIEW is used, coding was faster and debugging was easier. Experiment observed that with multi-layer Western kernel shows better accuracy than RF kernel. These are my references. Thank you.
Any questions? I found a lot of similarity with one of the earlier papers which were presented. Is it a joint work or something? Real-time implementation, or maybe the same problem. This target is what you identified shipment code and surface tab. You indicate your last shipment code. Thank you. Yeah, we move on to the last paper in this session. And L2 norm regularize standardized class with improve generalization capability. There are four authors: Sadish Chandran, Suraj Kamal, A. Mujib, and Dr. Supriya. And the paper is going to be presented by Sadish Chandran. He is a research scholar with the Department of Electronics, CUSAT. You have a 1 year experience as an assistant professor in CUSAT.
Good afternoon, everyone. I am Sadish Chandran, scholar, Department of Electronics, CUSAT, and my topic is an classifier improved generalization capability. Let me move on to introduction. These underwater recognition systems have been developed to analyze data using machine in order to detect, classify, recognize target signatures. And a classifier system should have an ability to learn characteristic acoustic signature of the signal from a set of known samples for the purpose of attaining a generalized model. The most widely used classifier is the supervised one, which is based on a set of finite target observations obtained a priori. And the learning task involved in classification aims to infer an estimator that can approximate an unknown functional relation or a mapping function between the observed signal and the corresponding class from the provided instance class pairs. And the desired property of the estimator is to perform well on a real target recognition scenario. That is, it should have good generalization capability. Hence, the problem of learning can be studied in the framework of inverse problems. But the problem associated with an inverse problem is that its solutions are often ill-posed. That is, many possible solutions can exist. As we know, the ocean ambience is a complex acoustic mixture which consists of several noise sources like ocean currents, coastal machines, offshore oil and gas production rigs, marine life, shore waves, etc. In addition to the reverberation, Doppler shift, spreading and intermodulation introduced by the jumbled channel. This increases the dimensionality of the vector to be measured, and it expands the solution space, that expands the number of solutions for the inverse problem. This makes the task of classification extremely challenging. What is the solution to this problem? We know that feature attraction of targets can be used to alleviate years of dimensionality and to yield better invariant representations for the signal. And these features are provided as instructions for a classifier. Although this feature can be solution to a certain extent, these solutions may not still be unique. In such case, the approximator overestimates the complexity of the problem, leading to a phenomenon of overfitting, which I will discuss in later slides. This overfitting degrades the generalization capability of the estimator, results in a significant reduction in classification for predictions on unseen target samples. So, how we will get an effective solution to this problem? To get an effective solution, this problem needs to be reformulated by including additional constraints such as the solution. This process is known as regularization. It shrinks the solution space and restores the stability of the solution. And the technique based on regularization involves minimization of an objective function, which is the sum of two terms, out of which the first term is the data fit term, tries to fit the data, and the second is a penalty that favors simple models. By introducing regularization, classification problem becomes well possible and it implicitly addresses the problem of overfitting. Now moving to the second stage, the target feature structure and measurement is to use lower surface by obviating the irrelevant information in the target signal. But the main purpose for us identify a representative set of discriminative features. The set of features identified for this project was zero crossing range, the rate of silent change along a spectrum like ratio of the geometry the meaning of the power spectrum, which corresponds to the fundamental frequency of the sound. It is estimated from the harmonic spectrum by downsizing targets and multiplying the result together, so that results in a formation of a strong peak at the fundamental location. Another feature is spectral roll-off, which is the frequency below which the amount of spectrum magnitude resides. And this specific amount has 85% for this work. Another feature is spectral central, determines the area around most of the signal energy is concentrated. Then efficient coefficient already discussed by the other, so I am not going into the details. After this feature extraction, these features must be normalized because different features may have different range of values. So we have to restrict the values of all the features to determine ranges. So feature normalization is carried out. And these are features how we normalize by using this formula. Standard deviation. After this normalization, we move on to the classification stage. And the classifier for this purpose is the logistic classifier because it has a low complexity and is less prone to overfitting compared to artificial neural networks. And consider a logistic classifier, M training sensors, XI are training and the YI are the class labels. Then the probability distribution for a class label Y, even if feature vector X can be modeled as like this, G of theta transpose X, which is equal to 1 by 1 raised to minus theta transpose X, where theta are the model parameters means slope and intercept coefficient for that model. G is the load or function, and the hypothesis of X becomes true when G of theta transpose X greater than or equal to 0.5. Let this phi1 be phi2 be that formula. Then the overall cost function can be derived through maximal estimation is written as J of theta is equal to minus 1 by m sigma is equal to 1 to phi1 plus. This is the cost function which needs to be minimized in order to optimize the parameter theta. Now coming to the problem of overfitting. This picture shows a regression model. In the first figure, we can see that for fitting that hypothesis is insufficient because that is theta of theta naught theta 1 x results in an underfitting of the data. That is data is not properly results in a high bias. And the last one we can see that hypothesis is overfitting of that data because tries to fit the training too hard, thereby using the generalizability of the classifier. Fails to generalize examples. So what we want the optimum is the middle one, which is just right. We need the right hypothesis. Even though plotting the hypothesis may provide an idea of a good fit, it doesn't work when we have large number of features. Because it is difficult to plot and visualize the data, decide what features to keep and which features to drop. In such scenario, the hypothesis may give a cost function of x0 by trying too hard to training set, and thus the classifier becomes unable to generalize to new examples, and these results may become erroneous. This is referred to as overfitting, which affects the generalization capability of the classifier. How we can avoid overfitting? In literature, there have been many methods suggested. One of these is reduce the number of features by manually selecting desired features or utilizing some modern selection algorithm to reduce the number of features. But when we reduce the number of features, it results in some information. What is the alternative method? It is regularization. In regularization, no features are avoided. Instead, the magnitudes of the parameters are reduced. Results in a simpler hypothesis and it was efficiently lots of features. Each feature contributing a little bit to predicting the class level Y. Moving on to regularization, what we have implemented L2 regularization. We can see that the modified function regularization is equal to minus 1 by m by y1 by 2, which is the data term. That is the first term in the regularization. And second, in the objective function, second term, lambda by sigma is equal to 1 to eta j square is the penalty term. Sigma is equal to 1 to eta j square is the square of L2 lambda is the one which introduces penalty to that term. Thus, the choice of lambda assumes great significance because very large of lambda penalize all the parameters. We have shown here the other graph with the very large values of lambda. The graph becomes like first one results under fitting of the data, and when lambda is small, it results in an overfitting or high variance. So we have to choose an optimal value of lambda to get the hypothesis of x. So the choice of lambda assumes great significance. Now, how we can minimize cost function? There is a method called gradient descent to minimize objective function, but it requires an additional parameter learning rate. So we have gone for Newton's method, very fast and efficient algorithm, and compared with gradient descent, there is no need for the learning rate. The updated rule for Newton's method is like this. Theta instant is given by theta percent minus inverse del theta j, where del theta j is the gradient, which is the first order partial matrix, and Hessian is defined as that one. Each element of Hessian is equal to del square theta of theta divided by dou theta j, second order partial derivative. Let's say delta be like that, and gamma be that matrix. Substituting value of j of theta, that is the modified j of theta, into this equation. Del theta j becomes like this. And when we substitute this value into the updated rule of theta, we get the value of theta iteration. And these iterations are continuing until we get a minimum function, and this cost function gets converged, optimizing the value of theta. Now coming to the results and discussions. The data set for this purpose consists of training and testing sets. For the training set was constituted 240 samples from each class, and test set 60 samples from each class. And the features extracted were zero flatness, speech, spectral roll-off, spectral central diagram, and 13 coefficients of MFCC, and tested spectral count 7 classes of vessels. And multi-classification, as discussed earlier, were implemented, which employs a one-person approach, employing 7 binary classifiers for this task. And coming to scatter plot of features, here is a scatter plot of 0 versus spectral roll-off, and we can see how those features are, because there is a little confusion between class 4 and class 7. Similarly, addition of other features to enhance discriminating capability of the classifier. Now testing for convergence of Newton's algorithm, the cost function is plotted against number of iterations. For lambda equals 1, we can see that initial value for iteration 0, initial value of 0.931, the algorithm converges 10 iterations with the final value for classifier 1.001 and for classifier 7.059. We must also evaluate how the algorithm converges to various values of lambda. For that, cost function plotted against number of iterations for various values of lambda. We can see that with increasing lambda, the algorithm converges very fastly. For lambda equals 0.001, it takes 16 iterations, whereas it takes 11 iterations for lambda is equal to 0.1, and for lambda is equal to 7, the algorithm iterates in 7 iterations. So 7 iterations. In order to access the performance of the classifier, receiver operator characteristics is shown. It is a two-dimensional depiction of classifier performance, and this expected performance can be converted to a single scalar value using an arrow seeker. You can see right, this class was 1177 and for the classifier 6 shown in black, this area that curve is very small. That means it has an inferior performance. By incorporating regression, you can see that graph moves up to the top. The area that curve gets increased, thereby improving the performance of classifier. Now by employing regularization, these parameters are told that 5 features and 30 MFC coefficients resulting in theta 1 to theta 18 features plus theta naught, which is a slope, which is an intercept coefficient. These are the parameters to be optimized, and the two magnitudes of the two values of these parameters are shown in this table. And you can see that with increase in increase in the value of lambda, see that lambda is equal to 0, we see that this magnitude is very high, and with increase in lambda, this magnitude gets reduced, which results in a simpler model, thereby avoiding the problem of overfitting. In order to test the generalization ability, the classification accuracy has been tested on test samples for various values of lambda. We can see that without regularization, that is for lambda is equal to 0, the classification accuracy is only 82.86%, and this accuracy increases for a wide range of lambda. And the maximum accuracy has been obtained for lambda value is equal to 0.001, and the accuracy falls below 82% for values of lambda greater than 100 because it results in underfitting of the data, thereby again losing the generalization capability, resulting in a highly biased model. Therefore, parameter values corresponding, that is theta values corresponding to lambda is equal to 0.001 provide an optimum bias trade-off, variance trade-off model for the trade-off of the classifier model. Now, getting into the conclusion, an effect of L2 regularization on the generalization capability of data classifier has been analyzed, and the classifier has been classifier based on logistic regression has been chosen for the purpose, and the cost function has been minimized using Newton's method, and the algorithm has been tested for various values of lambda, and it has been seen that this algorithm converges within a less number of iterations, optimizing the parameters efficiently. And the performance of the classifier has been visualized using ROC, and the regularization, the effect of regularization on parameter magnitudes has been analyzed. In addition, the model has been evaluated on new target signals, and its accuracy has been inspected for a wide range of lambda. It can be inferred from these results that regularization addresses the problem of overfitting, improving the generalization capability of the classifier, yielding better classification results. These are some of my references. Thank you.
Do you have any questions for the speaker? Looks like everybody's ready to go home. That concludes this session. Is there any announcements to make? Something is.
Okay.
We had seven papers in this session. I thank all the speakers for their crisp presentation and sticking to the allotted time, helping us conclude the session in the stipulated time. Thank you once again.
Now, I request our Chair, Shri Mohan P. Matthew, to hand over the certificate to our speakers. Let me call upon Sirisha from NIT to come onto the stage. Next, I call upon Kanan from NIOT to come to the stage, please. Sharon BM from Kusat. And next, Ritu James from Kusat. Now I request Session Chair Dr. Gopu Poti to hand over the certificate and memento to Alex sir. Next, I call upon Chichu to come on the stage, please. Satish Chandran from Kusat. Now I provide PRs to hand over the memento to our Session Chair, Sri Mohan Matthew. Now let us have a small break, and we have a cultural program at 6 p.m. Please stay back for our programs and for dinner at 8 p.m. And all the registered candidates can collect their seminar kit and proceed to the registration desk. Thank you.
Check.